Everyone, this is Patterson here, checking in with our lesson on 12B, geometric operations with vectors. My suggestion to you is that you might want to have graph paper with you as you go through taking notes on this section and also working on the assignment that will be coming at the end of this lesson here, because we're going to be talking about geometric properties of vectors. So what do we already know? We already know that if we're talking about traveling, say, 4 kilometers east and then 2 kilometers south, we could find how far we are from our original location. We could use the Pythagorean theorem to do that. We could also find at what angle we are traveling, just using SOHCAHTOA, simple trigonometry, right triangle trig, in order to find that. We already know these things here. And what we're doing today is we're taking vectors, which each one of those distances traveled were vectors, and we're going to be talking about how to describe where we're going, where we've been using vectors. So if we look at this particular example here on the right, we see vector PQ and we see vector QR. Notice I said PQ because the vector started at P and went to Q, and then this vector here started at Q and went to R. And what we're basically saying is that if I take vector PQ and I add vector QR, I'm really just talking about the same thing as the vector PR. So we can write these vectors in equations as we see right here. PQ plus QR equals PR. So if we're trying to do this, all we have to do is to draw vector A, and at the arrowhead of A, in other words, where vector A terminates, we draw vector B. And then all we have to do is we draw the beginning of vector from the beginning of A to the arrowhead of B, and there we have vector A plus B. So if we took this example here, we have vector A, which goes up 4 and right 3, and then from there we're going to put vector B on top of that, which is going down 2 and right 4. If we were to pick that up and put it on top, we would see that we would have vector A plus B right here. Now the zero vector has no magnitude. So if I say vector A plus 0, well, that's the same thing as 0 plus A. Commutative property holds with vectors. And that's the same thing as vector A because it does not change at all. And if I have the vector A plus the opposite of vector A, well, again, commutative property holds. And that's going to be equal to the 0 vector because I'm going away from A and then I'm coming right back to where it started. And therefore, the vector is the 0 vector. Let's take a look at this example using the polygon here on the right. If it says vector BC plus CA, if you notice here, the first vector ends at point C and the second vector starts at point C. So really, I can just say that by the transitive property, that vector BC plus vector CA is vector BA. If I look at vector BA plus AE, again, notice that they share that point A, and also here they share the point E going from vector AE to vector EC. So therefore, again, just skipping ahead, BA plus AE plus EC is equal to BC. And the same thing holds for part C as well. It's just going to be vector AA, which is 0. And if I look at D, again, everything holds, so it's just going to be vector AE. Okay, so now if I'm subtracting a vector, basically what that means is that I'm, just like if I were subtracting a number, that'd be adding the opposite of that number. So if I look at vector A minus B, that's the same thing as saying vector A plus negative B. And for the purposes of looking at them using notations, if I'm looking at vector AE and I want negative AE, that just means I'm saying EA. And so I'm just switching the order of the variables there. All right. So if I'm looking at here vector A minus B, well, here's A going up 4 and over 5, and here's B, which is going up 2 and to the left 3. So if I want A minus B, I can start by drawing A, and again, this is where the graph paper is really going to help out. Now B would have taken us up to left 3, but since I'm subtracting B, I'm actually going down to right 3. So therefore, vector A minus B is going to look like this orange vector right here. So if I'm looking for a vector R minus S, I'm going to start with R, and then instead of S going up 3 and over 1, it's going to go down 3, left 1. So r minus s looks right here. Sorry, that pops up every time. And if I were to just go a little bit farther, s minus t minus r, same thing. I start with drawing that vector s. Then instead of going down with the t, because I'm not adding it, I'm going to subtract it, which means I'm going up and to the right. And instead of going to the right, if I were to be adding r, I'm subtracting r, so I'm just going to the left 4 units. So therefore, s minus t minus r is this red vector right here. Now, if I'm subtracting vector AB minus vector CB, you'll notice that the inner two parts are not the same letter. So all I have to do is consider that I'm going to switch it. I'm going to switch the order of the second vector, make that vector BC, and add in between there. So vector AB minus CB is the same thing as vector AB plus vector BC, because vector BC is the opposite of vector CB. And therefore, I can say that vector AB plus vector BC is equal to vector AC. If I look at the second one here, it's really the same thing, except I have 3 vectors that I'm working with. AC minus BC becomes AC plus CB, and then minus DB becomes plus BD, and all the inner 2 points will match up, so it can be just vector AD. If I look at this one here, it says construct the vector equation. So basically, in this case, I'm doing the opposite. Instead of just looking at the diagram and finding out what vector will match some of them, I'm writing the vector equations myself. So in this case here, I have vector t, which is going from this point on the left down to this bottom point here. Well, that's the same thing as vector r plus vector s. So vector t equals vector r plus vector s. And similarly on the right here, if I were to look at starting up here in this top left corner, if I do vector d plus vector e, I end up in this bottom right portion. And that's the same point that I would end up with if I had vector g plus vector f. So vector f, well, this is a slightly different way to write it there. I could say that d plus e equals g plus f. And then if I just solved for f, I could just subtract vector g from both sides and have f equals negative g plus d plus c. It's an equation, so there's multiple ways that I could write this value here. And just a note, a reminder, you see here on our screen that it's showing a bolded f. When you're writing this in your notes, you have a hard time showing that it's bolded, so you put the arrow notation on top of the f there. All right, taking a look at vector rs here, and it wants it written in terms of r, s, and t. So r, s. Okay, well, there is no vector that's clearly marked right there using the r, the s, and the t. But if I wanted to get to r, s, I could go down to the origin, and then I can go back up to s here. So vector rs is negative r, because it's going in the opposite direction, plus s, or s minus r. Vector SR, just doing the opposite there, going from S to R, is negative S plus R, or R minus S. And ST, if I want to go from point S to point T, I'm going to use a negative vector S plus the vector T, so negative S plus T, or T minus S. All right, so I'm just figuring out how can I get from one point to another point using the vectors that they've labeled there for us. All right. Now, a scalar multiple. So when we're looking at these vectors, they have a certain length to them. They have a magnitude. And if I multiply that length by a certain value, that's referred to as a scalar multiple. All right, so it's not changing the direction at all. It's just changing the magnitude. So if I have vector A, and then I do 2 times vector A, well, that's going to have the same magnitude as A plus A, because A plus A is 2A. And it's going to go in the same direction as A. 3A, same thing. Negative 3A is going to be the same idea, except it's going to change direction here because I am multiplying by the negative there. So negative 3A equals negative A plus negative A plus negative A. All right. And again, we want to use some graph paper to help us with these diagrams here. Just the general idea here. If that scalar multiple k is greater than 0, then it's going to have the same direction. If it's less than 0, it's going to be in the opposite direction. And if k equals 0, then it will be the 0 vector, meaning it won't have any magnitude at all. Let's take a look at example 9 here. We have 2r plus s. So r goes up 2 and over 3. So 2r is going to go up 4 and over 6. And then I'm doing 2r plus s. So on my graph paper, I'm going to go up 2 over 3, up 2 over 3, and then I'm going to go down 2 over 2. And therefore, the red vector shows 2r plus s. Using the same idea with r minus 3s, r is going to have me go up 2, right 3, and then negative s is going to be applied 3 times. So I'm going to go, instead of down and to the right, I'm going over to the left and up 2, left 2, left 2, and then go from there, and therefore r minus 3s is the red vector here. All right. Here, we're taking it a little bit from a different point of view. It says sketch vectors p and q if p is equal to 3q. All right. Now, we don't know exactly what q is, but basically, if this were to be q, then p would be 3 times that. And the same thing here, p equals negative 1/2 q. If q is equal to this portion here, then negative 1/2 of that is going to be half the distance in the opposite direction. All right. So again, we don't know exactly what either p or q is, but if q is as we show here, that's what p would look like. So that's it for this section here. Kind of a lengthy assignment here, but none of it is tragically hard. Try to get this work done here and post it on Google Classroom for us. Hope you guys are doing well. Have a great day.